Okay. So yesterday we started the ETAP topic yesterday, and we discussed the ETAP software introduction, and thereafter we start the equipment modeling. And in the equipment modeling, we have discussed about the bus bar modeling and the power grid modeling, right? So any doubt, any query from the yesterday class? Any doubt, any query? So we discussed about the grid modeling, power grid modeling, and what the inputs we required X by R value and then impact of the X by R value. So all those things we discussed yesterday, and then how we can calculate the X by R as well also. So let us take today. Let us take today the next equipment. Next equipment as a, like we discussed yesterday about the grid. So we are modeling the power source equipment modeling. So in the power source, yesterday we model about the grid, and let us take today our conventional generator, our conventional synchronous generator that we use for the conventional any power plant to generate the power. So let us see how we model the generator in the ETAP for the load flow analysis or for the short circuit analysis purpose. So before coming on this in the ETAP, go to in the ETAP, and as we discussed that in ETAP we have readily available equipment symbols. So here if you see we have the symbol for the generator. So just click on this, it will be selected, and then you can anywhere you can drop it and drop it. And suppose now this generator going to connect on a bus bar. So here we drag and drop the bus bar. Okay. Now as you can see over here, let me drag it down so that we can make other SLT as well. So as you can see here, this equipment, it is not visible. So right click here, service in. So it would be like red color. So now one thing that here we have the bus bar and here we have the generator and their terminal coming this side. So for that purpose, just right click on this equipment symbol and then go to the rotate, and here we can rotate 180. So in that case, my terminal, it is coming this side, and then we can connect to this bus bar, and here we have the bus. So bus mod already we have model. Bus already we have model. So let us model this generator. Let us model this generator. Okay. Let us model this generator, and let us see how to model this. So first is the info page. So here the generator ID and which bus it is going to connect to that bus directly we can select from here as well. The generator like tag number, name, description. So this all we can mention over here. Then condition service in and out. So that would be in service in. Then status as built, configuration normal, operation mode. Now you see here, it is not coming by default in swing mode, it is coming in other modes. So yesterday we discussed that the grid we take in swing mode, but generator we do not take in, we can take in other mode as well, like voltage control, MR control, PF control. So we'll discuss today about all this operation mode as well. So with out of this one we have to select, and thereafter we have to go into the rating page, and here we have to select the ratings like megawatt or kilowatt. So here you click, so it will convert from megawatt to kilowatt. So here we have to mention the megawatt of the generator, then generator output voltage. So this kV we have to mention, the power frequency here we have to mention, power factor here we have to mention, power factor efficiency here we have to mention. So all this we have to mention. So let us see one by one the basic concept, and thereafter we will come again on this ETAP window and we will model here. So but first let us see how we are selecting the value, or what is the concept behind the values. So let us start with the generator modeling. So and before modeling, let us see what mean by the generator. So the synchronous generator, also known as an alternator, is an electric device that transforms the mechanical energy uh, from a prime mover into the into the AC electrical power at a specific voltage and a specific frequency as well. So this is a basic difference about the generator. As you all know, this is your college time, you have a study about the generator. So same things, just a brief intro what we have discussed about the generator, their definitions. So let us see one by one. So generator modeling in ETAP. So this page I have taken the first page. The first page I have taken the snapshot, this info page. So this I took here and I paste over here. Info page. So here ID, bus, each and everything. Same as this. So enter the unique ID with up to 25 number characteristics we can put over here. So ID we can put over here and up to 25 alpha numeric characteristics we have limit. So up to that any ID we can put as per the project specifications. Our project SLD drawing we can put over here. Thereafter, conditions, so that would be obviously service conditions, service in and out. Service, the operation conditions can be set by clicking on the button for either in service or out of service. So generally we take in service. State is used to describe the services status of an element. So state will go with the as built element. So in the element tag number description, so tag this allow the user to enter a feeder tag in this field using up to 25 alpha numeric characteristics. So up to 25 we can put here the ID, the tag of the generator, the name. This allow up to user to enter the equipment name, up to 50 alphanumeric characteristics. So name and description we can put over here. This is about our naming of the generator in the software. Thereafter we have this operation mode, swing, voltage control, MR control, PF control. So let us see one by one each mode, their meaning, definitions, and then we will select. So swing mode, already we discussed, used only when so when we select the swing mode, and so this used only when we have only one generator and are feeding the loads, and there is no grid supply is available at that generator connected bus. So if there is no any grid, in that case, to converge the load flow, one source we have to take into swing mode. So due to that reason, since only we have generator as a source, so generator operation mode we have to select into the swing. If in case there is no any grid available. But if grid is available, in that case, my generator will go in other mode like voltage control mode or other mode, and the grid will be operated in the swing mode. Now let us see what is the meaning of swing mode, voltage control mode. So if a grid and generator are connected to a common bus bar, the generator should be operated in the voltage control mode and my grid will operate into the swing mode. All large scale generator can be put in voltage control mode. So like large scale megawatt scale generators, we generally take under voltage control mode so that they can regulate their output terminal voltage. By adjusting the active or reactive power, they can maintain their voltage, 100% voltage, their terminal voltage. So we take generally generator in the voltage control mode. A generator can be selected as a voltage control and voltage controlled, or we can say voltage regulated system, which means that the generator will adjust its var output to control the voltage. Therefore, the generator's terminal voltage magnitude, generator operating real power, and minimum and maximum allowable reactive power supply, max Q and minimum Q, must be entered for the voltage control generators. So for that reason, if we are selecting this voltage control mode, thereafter my next work would be, my next step would be going into the rating. Here we have to put the rating, and after putting the ratings, here we have to mention my generator maximum reactive power limit and the minimum reactive power limit, Qmax and Qminimum. This also we have to enter over here. We'll come later on about this limit, how to decide it. But Qmax and Qminimum also we have to provide there. Then it will work in voltage control mode. Then we have MR control mode. So using this option, we can specify the amount of fixed megawatt and fixed watt generation in the range, in the rating page of the synchronous generator editor. If it is required, then in that case, this could be selected. PF control mode, the generator's megawatt and percentage power factor setting must be entered. on the rating page for the generation category selected when model in this mode. But this is the options we have, but generally for the large scale generators, we go with the voltage control mode. But MVAR control and PF control mode options also available. We can model this if in case it is required for any specific project. So this is my info page. This is my info page. In that we have discussed all the parameters, what parameters we have to select. So going to here and then info here. So ID, we can put any ID here. Bus tag, name, description, status in configurations, voltage control, and then click. Then this is my info page is completed. Then go to the next rating page. So here in the rating page we have to enter all the data like megawatt, kilo voltage, power factor, MVA. This all MVA if you're not putting, if you're putting the kilo voltage and then megawatt, MVA could be calculated, and power factor. So MVA it will automatically, it can calculate as well. So otherwise we can mention the MVA as well. Efficiency, if we know the efficiency of the generator, that we can also mention the poles level, the 2 pole or 4 poles, and RPM it will automatically calculate, and full load ampere it will automatically calculate. So this all we have to mention here, and then we have to mention here Qmax and Qminimum value as well. Okay, so going to the next rating page. So here we have the rating page snapshot, and you can see over here all these yellow parameters we need to define. So on the rating page, specify the power rating, megawatt or kilowatt, the output voltage, and the power factor data. Power rating kilowatt, megawatt, enter the rated real power of the generation in megawatt or kilowatt. Choose from those two options by clicking the megawatt or kilowatt button. So what I mean that here, if you want put into the kilowatt, so just click over here. So this will convert into the kilowatt. If you want to put in megawatt, so click here again, it will switch into the megawatt. So this you can like switch there. And voltage rating, we have to enter the rated voltage of the generator in kilo voltage. Generator voltage we have to mention. Then PF into the rated power factor of the generator in percentage, like 85% and 95%, whatever, or 80% power factor we have to mention over here. Generally for the large generator, the 80 or 85% power factor we take, isn't it? Right? The power factor.
Yes, sir. Normally we have used zero point 0.8 power factor for a generator. It's a generally we use zero point 0.8, no?
Yeah, 0.8. Yeah, that's, I'm telling, 0.8 means 80%. So generally we take 80 or 85% power factor for the generators. So zero point 0.8 we do not put, we mention here in the percentage. So zero point 0.8 means 80%. So 80 or 85%, whatever the power factor you are taking, that we need to enter over here. Then MVA or KVA, that we can enter over here. Efficiency, if of the generator, we can mention over here. Then poles, like generally we take 4 poles or 2 poles. So whatever the poles we have, enter the, generally we take 4 poles. So 4 poles we have to enter over here. Then RPM, they will automatically calculate like 120 of divided by P. That is the formula. So 120 into F, which is 50 Hz, and then divide by 4. That will be the RPM of the generator, right? So RPM, and then minimum and maximum Q, that you can see over here, Qmax and Qmin. So this value also we have to enter over here. So let us see this Q.
Sorry, sir, can you please repeat again RPM calculation? We have
Nothing, na,
divide
120 of divide by P,
120 divided by power. Okay, sir. Okay.
the same formula that we studied in the college time.
Yes, yes, sir. Sorry,
120 into
sir.
frequency divided by pole.
Yes, sir. Agreed, agreed. I will understand it, sir. Thank you, thank you.
Yeah, Roman. So this RPM, that 1500 RPM. Okay, and then Q max and Q minimum we have to enter over here. So before putting the Q max and Q minimum, that I can directly put, it will take just 1 second. But I wanted to go in deep about the Q max and Q minimum. So after understanding it in the depth, then we'll enter this value, so that you have the basic understanding that why this value we are putting and what is the concept behind this value. For the generator modeling, this two parameters is very important parameters, and most of the time I have seen that engineers are getting confused how to put the Q maximum and how to put the Q minimum. So first of all, this value we get from the generator manufacturer data sheet that we can put over here. But in case we do not have the generator data sheet and we are doing the system studies without the generator data sheet are given by the generator manufacturer, in that case we can also calculate it Then how to calculate it? So before the calculations, let us see what is the definition of this Qmax and Qminimum. And before coming to these definitions, let us see what is leading power factor, what is lagging power factor, what is unity power factor, and let us see the phasor diagram. And before, after understanding the phasor diagram, then we will understand the leading and lagging power factor, and then we will understand the Q and Qmax and Qminimum. So first of all, you are understanding what is the Q. Q means your reactive power, right? Isn't it? So
Yes,
here,
sir.
here you
Yes, sir.
mention,
Yes, sir.
here you mention megawatt. So this megawatt is your, this megawatt is what power? What
Real,
power?
real
Reactive
power.
Real
power.
power.
Real
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 power.
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 Here you mentioned the real power, and here you are mentioned, here we are discussing about the reactive power. So reactive power, here there is two things: maximum reactive power and minimum reactive power. So before coming to this minimum reactive power, let us see their basic concept. As per capability curve, correct, Sagar? As per the capability curve, this value we will get. But if in case we do not have the capability curve, in that case, how to proceed with the ETAP simulations, ETAP modeling? But yeah, you are correct. As per the capability curve, we have to mention over here. But in case we do not have, then how to put this value? So let us understand the phasor diagram of the system. So in the phasor diagram, as you know, that we have unity power factor, we have lagging power factor, and we have leading power factor. So here I have taken the phasor diagram, like we have the phase voltage, and then we have the current. And then this is my IARA, it is my real power. So the generator has different phasor diagram depending on the power factor. So unity power factor, so in case of unity power factor, current is in the phase with voltage. Current and voltage both in same phase. As you can see, current and voltage both in the same phase. IA is my armature current, and VA is my phase voltage. So it is my phase voltage V here. So the current and voltage both are in same phase, and the reactive part is exactly 90-degree perpendicular to the active part of the system. So it is my active part of the system. IARA or active power or the real power, and here this JIA into XS, it is my synchronous reactance power, reactive power, which is 90-degree in the angle with the active part of the system. Now, this is one case when we have the unity power factor. And then if we check EA is my internal generator voltage. So that would be my summation of the like active and reactive both power. And then here we have the my generator internal generated voltage here. Now let us take the lagging power factor. So in case of the lagging power factor, again we have the voltage and then current, and current is lagging with the voltage. So current lag voltage by some angle, and from the same imaginary part you can see the current lagging from the voltage. So when my current is lagging, so my active part is also coming over here, some lagging, and from that active part, the reactive part is 90-degree again 90-degree here. The reactive part exactly 90-degree perpendicular to the active part of the system. If we see the phasor diagram at lagging power factor, the generator terminal voltage means the phase voltage V, the generator terminal voltage or phase voltage V, or generator terminal voltage V is less than the induced voltage. EA is my induced voltage, internal generator voltage or induced voltage. So my generator terminal voltage is less than the induced voltage in generator, induced voltage in generator EA. Hence, if generator operate or run at lagging power factor, the generator has to supply more reactive power to the system, and this is called as Qmax value of generator during the generator modeling. are the maximum reactive power. So why they are supplying in order to like maintain the terminal voltage. The general terminal voltage is less. Phase voltage is less than induced voltage. As you can see over here, my generator voltage is less than the induced over voltage. So in order to maintain the terminal voltage, hence if generator runs at lagging power factor, the generator has to supply more reactive power into the electrical system network or into the system, and this is called as Q maximum value of generator during the generator modeling in the ETAP, because it is supplying, and this is also called the over excitation limit of the generator. Over excitation limit of the generator. This is, I hope you have heard this word, over excitation and under excitation of the generator. So this kind of the situations, when the generator runs in this kind of the situations, then generator is running over excitation state. Then we have the under excitation state. So in that case, like this case occurs when we have the leading power factor. So again, we have the voltage, phase voltage, terminal voltage, and then we have the, suppose we have the leading power factor. In the leading power factor kind of the load, my current is leading by some angle with the voltage. So current leads voltage by some angle, and from the same imaginary part, the reactive part is exactly 90 degrees. So my, like here I have active part IA into RA, and from the same 90-degree angle we have my reactive power. So now coming over here, it is my EA, which is the generator internal induced voltage, EA, internal induced voltage, to the active part of system. And if we see the phasor diagram, at the leading power factor type of the load, when generator connected, the induced voltage in the generator, induced voltage in generator is less than the generator terminal voltage VA, phase voltage V. Hence, if the generator runs at the leading power factor state, the generator has to supply less reactive power, because my terminal voltage is almost maintained, and the generator has to supply less reactive power to the system, and this is called as Q minimum value of the generator during the generator modeling. And this operation also called as under excitation limit of the generator. So this is a under excitation when leading power factor connected to the generator, and when lagging power factor, then this is called as the over excitation limit of the generator. There might be some confusion with this. So let us see with some other word, some other definitions by the for this Qmax and Qminimum. So I try to explain the Qmax and Qminimum with help of the phasor diagram, with help of the lagging power factor. Lagging power factor means my Qmaximum, and leading power factor means my Qminimum. Let us see with other way. So also it can be defined as this Qmax and Qminimum is the as minimum and maximum MVAR, RQVAR, or reactive power limit, the reactive power limit. This specify, and further this Qmax and Qminimum, this specify the minimum and maximum limit for reactive power generation. Minimum and maximum limit for reactive power generation. In other words, we can say that the generator not only supplies reactive power, as you can see here, we are putting the power over here. So they not only supply the real power which we are putting over here, the generator not only supply the real power. Along with this generator, generator not only supply the real power, but also it can supply and it can absorb as well, absorb reactive power within its capability, and the capability given by the generator manufacturer through the capability curve. Therefore, the Qmax is how much reactive power the generator can provide. The Qmax is the how much reactive power generator can provide or can supply into the electrical system, and Q minimum is how much reactive power the generator can absorb from the system in order to maintain their terminal voltage. How much reactive power generator can absorb. These limits are required for generator types and should be obtained from the generator's capability curve, as we discussed in beginning. As and this capability curve is provided by the generator manufacturer by their technical data sheet. But if they not provide, in that case, based considering the power factor, the maximum and minimum power factor, we can also model this value in the ETAP. So in the absence of manufacturer value, this can be calculated by the maximum and minimum power factor limit or leading and lagging power factor limit of the generator. For Q maximum, we consider the minimum power factor. Or lagging power factor. So this sentence you can again correlate here with also here. The for Qmax we consider the lagging power factor. For the Qmax value. We consider the minimum power factor or lagging power factor limit. Generally, the minimum power factor of the generator is in the range of 80 to 85% or 0.8 to 0.85. So, in that case, we have to select here this my power factor, which 80 or 85% that we need to put over here. And for Q minimum, we consider the maximum power factor limit or leading power factor limit. And generally, this 0.95 or 95% value we take for the maximum power factor, and corresponding to that, we get the minimum reactive power. And let us see a quick view of the generator capability curve, how it looks like. So you can see it is the a generator capability curve, like image, one example of the generator capability curve. So the generator capability curve is a semicircle. As you can see, the generator capability curve is semicircle drawn with an upper and lower limit, lower power limit diagram. As you can see over here, it is my maximum reactive power Qmax, and then here we have my Q minimum reactive power. Reactive power, and when generator is operating above this limit, then we telling that generator is operating under over excitation limit, overexcitation here. And if in below this minimum reactive power, then it is a under excitation limit. And here I have my output power max output power, this one. So where point b to d b to d b to d, as you can see, this point b to d is the maximum turbine limit of the generator or prime mover limit of the generator. B to this point. The point B to M, this one is the maximum reactive power limit that generator can supply to the power system network, to the grid system. How much reactive power they can supply. The point D to Qmin, point D to Qmin is the minimum reactive power Qmin limit of the generator that it can observe from the grid. The red line shows, you can see here, over excitation limit of the generator, and the blue line, as you can see over here, shows the under excitation limit of the generator. And PE is the real power output that a generator must deliver. So this is a example of the generator capability curve. So when we do the project, similar kind of the capability curve is provided by the generator manufacturer. So from that capability curve, also we can take directly the Qmax and Qmin value, and we can enter over here. Qmax and Qmin value we can enter over here. This is the way that we do the project. But in absence of this capability curve, by considering the maximum and minimum power factor limit, we can also calculate the Qmax and Qminimum value, or it will automatically calculate it. So for that, let us how to model it. So in ETAP, to calculate the minimum and maximum reactive power, let us take a 100 megawatt generator. So let us take a 100 megawatt of the generator. So click over here, then voltage control here, operation mode, then go to the rating, and take this into 100 megawatt generator. Let us consider that this generator output voltage is 21 kilovoltage. 21 kilovoltage. Let us consider the power factor as 85% power factor, right? Let us see this. So my MVE automatically calculated. 4 pole we have mentioned, so RPM and full load ampere generator will automatically calculated. Now here I have to adjust. So for that, here like I am considering 100 megawatt generator. So in generation category, here we have to come in this option, and here we have to enter megawatt. My generation megawatt is 100 megawatt over here. Then in that case, and for that we see here it is not coming anything. Here no any change coming over here. Why it is not coming over here? Because I have taken generator into the voltage control mode. So in order to get the reactive power maximum minimum limit, I have to go back into the info page, and this operation mode I have to change from voltage control mode into the power factor control mode, PF control mode. Thereafter we have to go again into the rating tab, and then again here we have to put 100 megawatt, and then power factor here I am putting like 85% power factor. 85% power factor. And then in that case you can see my MVAR how much it is coming. 61974 automatically ETAP calculated, isn't it? 61974, 185 I consider here, right?
Yes, sir.
So that
Yes,
value,
yes.
that value I have to enter here. So 30 I have to change, and I have to mention 61.974. It is my Q maximum value. Now suppose I'm taking this generator, the maximum power factor is 95%. Maximum power factor is 95%. So please correlate this maximum power factor and minimum power factor with my phasor diagram to understand to that Qmax and Qmin value again. Suppose I'm taking this generator, 100 megawatt generator, operating maximum power factor, leading power factor is 95%. In that case, the MVAR value, it is coming 32868, that it have automatically calculated. So now we have to go into Q minimum, and here we have to put this value, and see this value. Q minimum value always we have to take into negative 32.868. Why it is into the negative? Why I'm putting here negative, or why I'm telling that I have to put this value into the negative sign? Why with negative sign? Q minimum, why negative sign with the Q minimum?
Because this much
Absorbing.
power
Because
is
it goes to
generated
under
will
the
absorb.
zero, sir.
Receiving
It's a leading
the
power factor. This is called leading power factor.
maybe generator is receiving the reactive power.
Sir,
This much
it's a
power is
reactive
getting
power,
absorbed
na?
by generator.
When we
Due to
when we
observing,
minus,
due to observe. So observing means
Yeah,
negative.
yes, due to observe. Reactive power here also, but I now do not put negative here, but here I am putting negative here due to observe. Let us see this. I am mentioning here. So in ETAP, to calculate the minimum maximum reactive power, let us take a 100 megawatt generator operating in voltage control mode, generating power at 21 kilovoltage level with a minimum power factor of 0.85 or 85% and maximum power factor of 0.95 or 95%. So maximum and minimum and maximum power factor we also get from the generator manufacturer. Okay, so we consider this, then we put the value here, and then go to the info page, change the operation mode into the PF control mode, and then come back and put our value over here 100, and then it will telling you the MVAR value 61974. As you can see, 61974, it is coming here. So that would be my Qmax. So I have to copy this data and I have to paste under the Qmax column. And then I have to put power factor, maximum power factor, leading power factor, 95%. Then again, ETAP is suggesting us the MVAR value. So this value we have to take, and we have to put under the Q minimum column and with the negative sign. So change the operation mode to PF control mode. Then again go to the rating pace tab and enter the rating pace tab. Then enter the megawatt value as 100 megawatt as we mentioned over here. After that, MVAR will calculate by ETAP itself, and that will be Qmax value. The same we need to enter in the Qmax column, as you can see over here. Now suppose the generator's leading power factor or maximum power factor is up to 95%. Then enter the percentage power factor is 95%, as you can see over here. ETAP calculate the MVAR as 32866 over here. The same value that needs to be entered into Q minimum column with a negative sign. Minus 32866. We need to enter Q minimum always with negative sign. So as all of you telling that Q minimum always negative sign. The reason because Q minimum always with negative sign, because the role of generator is to supply the real and reactive power to the grid, to the load, to the network. But instead of supplying the power, if generator is consuming the power or consuming the reactive power, which is against the generator's nature, or opposite operation of the generator, Therefore, we should use the negative sign with the Q minimum value, right? Isn't it? Right? Am I clear that why?
Yes, sir. Yes, sir.
Why Q
Yes, sir.
minimum?
Yes, sir.
Because it is the opposite operation. It is against the generator's nature. Generator nature is to supply the power, real and reactive power to the system, to the grid. But instead of supplying the power, if generator is consuming power or absorbing power, and that is the against the generator nature or opposite of the generator nature. So when it is opposite of generator nature, so we have to mention the opposite sign or negative sign with the Q minimum value in the column. So due to that reason, this value always we enter into minus 32866 with the negative sign. Thereafter, once we have mentioned the Q minimum and Q maximum value, so in that case, since we do not have the capability curve based on the power factor, we calculated the reactive and the maximum and minimum reactive power. Thereafter, if we want, we can go and this capability we can also set over here. This the capability curve. This we also can define based on our reactive power. So like I'm taking here calculator Q, or you can go with the defined QA as well. So QA is how much power, MVAR power it is generating 61.974. It is my QA. Same we can take generally nearly we can say QB as well. Similarly, QB and then QC. QC how much? It is in the negative. How much QC? Like we calculated
Minus 32.
QC value is the reactive power output. QC is the reactive power output. So it is
Minus 32.87.
32.877. It is my QC. And then QD generally we take nearly 2 times of the QC. So QD we can take like here QD, and then QD generally 2 times we take here QD, and then P minimum output power we have to define some value. So I'm putting just here 20. So here A, QB, QC, and QD. QD would be nearly 20 times. So it is nearly 20 times. So minus 32 nearly 20 times would be 64. So I'm going just nearly 2 times. So 60 I'm putting over here. So this kind of the curve in ETAP we can also model. It is near to the generator capability curve. So here I'm taking the this Qmax and Qminimum reactive power we can the capability curve we can draw. Otherwise, we ask the generator to plot the capability curve, and based on that we mention this value, and accordingly we mention the Qmax and Qminimum value also with the negative sign. Okay, but in absence of that, this is how we can also model. and then go back, and then we take into voltage control mode again. Okay, okay, and then run. So let us consider, let us consider this. Now we have modeled this generator. So let us consider that this generator is connected to a bus. So let us take this bus. So my bus voltage is also 21 kV because my generator voltage is 21 kV. So connect to this bus bar. Connect to this bus bar here. Connect to this bus bar over here, and thereafter let us consider that this generator is transmitting a 400 kilo voltage to a power grid. So generator output voltage is 21 kV. So we have to take a transformer, and this transformer, like suppose since 100 MVA I have taken, so we have to take transfer power more than 100 MVA. Let us take, I am going with the 150 MVA, and let us take that 21 kV it is taking, but my output voltage is 400 kilo voltage, 400 kV, 400 kV. My generator voltage, transfer primary voltage, then impedance and all those things we can go with typical. I will take this all settings separately. I will take all this transfer modeling separately just after this generator modeling. So I'm just going with some default value, and then let us I'm just wanted to like calculate. uh, we have modeled the generator. Now how generator is behaving with the grid. So for that I'm taking one a small piece of the network. In that, generator is connected to the grid. So let us, here we have generating power plant, generator, then generator step up transformer, and suppose this step up transformer connecting to the grid, but grid is not uh, in the generator compound. Grid would be away. So suppose from the generator, let us take a transmission line. Let us take a transmission line. Let us take a transmission line, and transmission line is connected with the grid, system. So I'm taking a transmission line, and it is connected with the grid. Okay, let us take a transmission line, and my generator is feeding to the grid, this grid. Okay, so let us take this transmission line. Length is 100 kilometer length, 100 kilo, because 400 kV, so that would be a like medium or long transmission line. So let us going with a 100 kilometer transmission line, and then parameter, here we can define the parameters of the this conductor parameter of the transmission line, and the either option we can go directly in the impedance. And here instead of take a calculated value, because if we select here the parameter, the ETAP will automatically suggest the conductor impedance. But instead of taking, we can also define our define our based on our project transmission line parameter, we can define over here. So let us go with the user defined, not the calculated, and let us take my this transmission line impedance. So resistance, like positive impedance, positive sequence impedance is 0.1 ohm, and this is per kilometer, very small resistance at the temperature T1, and same let us consider same as the temperature T2 as well. Let us take this reactance as 0.3. Let us take this acceptance Y as some typical value just for our simulation purpose. Same value we can enter in the negative sequence as well. For any static equipment, positive negative sequence both are same. So 0.1, and transmission line is a static equipment, so positive negative would be similar, and X again 0.3, and Y again we can go with 3.6. Let us go with 0 sequence. 0 sequence generally 3 times of the positive sequence, so 0.3 over here. Resistance again 0.3, and X, let us take some value over here, like 1 point, generally 3 to 4 times. So let us take some value over here. and susceptance, let us take some typical data over here. So here, this is how we defined a transmission line conductor impedance. But for the real project, we have to ask this parameter from the transmission line contractor company, and accordingly we have to mention over here, or from the client, and then we have to mention over here. This is like our transmission line, 100 km transmission line, and it is connecting to the bus bar here, substation bus bar, and then to the grid. So let us take this bus bar is also on the 400 kV bus bar, and this grid is also 400 kV grid. 400 kV grid. Okay, so we are trying to understand the generation operations with help of some a piece of network. Okay, so here we have taken the generator voltage control rating. I have put over here 61 minus 629. Let us take this value as initially. Suppose we have not assigned any value over here. Suppose I am going with the without any value. So suppose I delete this value. So in order to delete, I cannot delete it. So I have to put 0 over here, and then 0 over here as well. So let us see that if we do not define any Qmax and Qmin value in the generator model, then if we run a load flow, then what would be the result in the load flow? And then we will see that why this Qmax and Qmin value we need to define. Okay, so then we have defined the parameters for the generators. For the generator voltage control mode, rating 100 megawatt 21 kV. Here 0, right? My bus voltage again 21 kilo voltage. My transformer is 21 by 400, 150 MVA transformer. Impedance and other things we are going with the typical. Okay, so thereafter transmission line, and then this 400 kV bus bar, and then we have a power grid which is again 400 kV. Without Q load flow would not happen. Yeah, Rasanta, let us see this, that whether it is happening or not happening. Yeah, you're correct, but let us see this. So if we run this load flow, just taking that how much load flow means how much power flow, so if we run the power flow, let us see what result is coming. Bus kilovoltage is bus kV is out of 40% range from the bus nominal kV. Bus 70, what is the problem with the bus 70? Bus 70, which bus is the 70 bus? Okay, this bus is 70 bus. So this is again 400 because there is a node. So this node also we have to define. This is a node, but this is a kind of the bus. Then let us see what the result coming. Okay, so let us as of now, let us take this result into MVA. Okay, let us see what is happening. It is my transmission line. Okay, here we have the generator. So what we can see over here, first of all, there is and in the voltage control mode, Qmax and Qminimum that I'm putting as a 0. Okay, and if we see here, this generator terminal voltage is increased from 100 to 100.84%, and there is no any reactive power flowing. Same thing we have mentioned over here. So this capability curve we have discussed. So let us see if we don't enter the minimum maximum reactive power in the generator, then what happens. For that, let us consider the same 100 megawatt generator generating voltage at 21 kV connected to a 150 MVA transformer for step up power at 400 kV and feeding to the grid through a 100 km transmission line. Minimum reactive power value is selected as 0. Here we are putting all the value as 0. Here all the values I am putting over the 0. Here everything is 0. Here let us put this value also as a 0 value. Reactive power not flowing, some active power is flowing, 100 megawatt. But now if I deleted this active power here also, active power deleted, megawatt real also I deleted over here. Qmax and Qmin is 0, 0, nothing. Everything is 0 here. Suppose we have not modeled anything over here. Only we have modeled the rating of the generator. And then when you perform the load flow analysis, when load flow converge, then you see there is no any power is flowing. There is no any power is flowing. Right? 0.0.5 megawatt. What is this power? What is the meaning of this? It is my bus voltage, which is 100% to the grid side and 100.54% to the generator side. What is this power flow? I'm telling there is no power flowing from generator to the grid, but you can see some power flow over here.
Due to charging. Transmission line.
Yeah, transmission line. Yes, transmission line power flow due to the charging current. You can say it is your line losses as well. So that line losses, that only power flow from the grid side, you can see it is flowing from the grid side to the transmission line. Whereas from the generator side to the grid, ideally the power should flow from generator to the grid. But if I do not model anything here, if I model everything, rating also I model everything over here. But if I do not model here, in that case, no any active or reactive power is flowing from generator to the grid network. So what is the use of this generator when the generator is not contributing any power to the grid? So it means in order to get the generator contributions, here we have to define each and everything, Qmax and Q minimum rating. Then only generator will contribute in the grid. So, and at the same time, you can see my generator terminal voltage is also increased from 100 to 100.54% is also. The voltage is also increasing. Okay. So for that purpose, we need to define here the Qmax and Q minimum value. So when minimum maximum reactive power value is selected as 0, then after the load flow, there is no active or reactive power flow occurring. And at the same time, as you can see here, at the same time, the generator bus voltage also increases because you can see 100.5%, it is increased 0.5%. Bus voltage also increases because we have not entered any scheduled power in the generator. Therefore, to avoid these conditions, it is compulsory that we have to enter the minimum and maximum reactive power value during the generator modeling. I hope you are now getting that why this parameter we have to define over here. Now, as already we discussed how to define these parameters and how to calculate this parameter, already we have discussed it. So let us define this parameter. Now when the Qmax and Qmin value are entered, let us enter this value. So go over here, and then go to the PF control mode, and then rating. Suppose I am putting the megawatt is 100 megawatt. Then in that case, what is my and power factor? How much?
0.85.
Yeah.
0.85.
85 because in the percentage, so percentage means
Yeah,
85.
85.
So Qmax is then it is coming 61.974 Qmax value.
Yes.
And then again change this power factor from 85 to maximum limit, which is my 95 percentage power factor, 0.95. Then whatever value coming, this value
Minus 32.87.
minus 32.868 or whatever 868, that we have to put over here, and then click on the OK, and then again run the load flow. Run the load flow here, and I need to select here voltage control mode again, and rating that we have mentioned over here. Run the load flow. Then we can see here and let us see the megawatt and then MVAR as well, both the active and reactive power. So you can see over here, now my bus voltage is changed from 100.5 to 100%, right? And now generator is also contributing in the grid. Generator is also contributing. But if you see here, what they are doing, they are contributing 100 megawatt, which is good. They're contributing 100 megawatt, 100 megawatt. They are contributing. At the same time, you can observe negative 8.2 MVAR. What is this negative 8.2 MVAR here? The reactive power
The reactive power is absorbing by the generator.
by the generator. But why they are absorbing this? Why they are absorbing this? Why they need to absorb, consume from the grid? And how
Maybe
to,
the induced volt.
how to fix this? How to fix this?
Reactor.
How to fix
Minus
this?
means export.
So first, for this to fix this, to get the this actual active and reactive power, what we have to do? My transformer, because reactive power is depending on the voltage as well, my transformer go to the rating, and here I mentioned the primary voltage is 400 kilovoltage. Here I have to mention the maximum primary voltage or rated voltage. So for 400 kV, what is my rated voltage or no load voltage of the transformer? Or rated voltage, how much?
4 to 5.
420, right?
5.
420. For
Yes,
400
420.
kV, for 400 kV it is 420.
Just
420. 400 kV, but nominal voltage is 420.
420. So if I mention now 420, then click on the OK. Then click on the OK, and then go again. Click on the P and Q power flow. P is real power, Q is the reactive power. So click on the real and reactive power flow. So here now go here P and run the active and reactive power flow. Run here. Now you see here. Now the generator in earlier they are absorbing or consuming 8.2 MW from the grid. Now they are supporting to the grid. Now they are supporting to the grid. So whatever the reactive power required, because my generator capability limit is 61. So up to this much power they can supply, they can provide to the grid, right? So now they are supporting to the grid, and they're not absorbing the reactive power. Now they're operating at 100 megawatt, 13.77 MW. They're like feeding to the grid system, and my generator grid voltage is 100%. This is case one. Case one, uh, when my grid voltage is 100% voltage, and my transformer. So this, let us copy this, and let us take some case two as well. So Control C, and then paste here. So for the paste, right click, and do not put Control V, because one version has been copied in the dumpster. So whatever the version copied in the dumpster, that I have to move here. So for that, do not put Control V. Select here, move from dumpster. Move from dumpster. Okay. I did not copy it. So first of all, select the whole system, then Control C, and then do not put Control V, right click, move from dumpster. So the whole system we can copy now over here. So suppose it is my case one. Suppose it is my case one. Suppose it is my case one. Let us move the whole system. Whole system over here. And suppose it is my case one. Case one. Case one. And in that case, my grid voltage is 100%, which is not the ideal case. Always grid voltage is 100%. Grid voltage will also fluctuate, but let us see, the grid voltage is 100%. Okay, now let us take the second case. Now again Control C and move from temperature. So case 2, grid voltage is not 100%. Suppose grid voltage little bit increase. Suppose it is little bit increase in the night time. Grid voltage going 102%. Why it is increase in the night time? Because my night time and my load is less. So when load is less and my transmission line is also injecting the reactive power, load is less. So in that case, my bus voltage or grid voltage is going to increase. So grid voltage, suppose it is boost up to 102% at the night time, and for that purpose we have to go into rating, and here I have this 100%. I have to change from 100 to 102%. Then only it will be 102%. In that case, what is happening? Let us run again the load flow. So you can see here now, in order to support the system and to maintain the grid, the generator output voltage is 100%. Now if my grid voltage 100 change to 102%, the generator output volt reactive power change from 39.7 MVAR to 20.6 MVAR, and again they are maintaining their terminal voltage is 100%. Same thing we have mentioned here as well. So now when the Qmax and Qmin value are entered in the generator injects 100 megawatt into the grid and at the same time absorb 8.5 MVAR from the grid. So now when the generator can supply 61.974 MVAR, so by absorbing 8.15 MVAR from the grid, so this is our earlier case. So this is due to the HV side rating of the generator transformer, as here we have selected 400 kV, so that we need to change to 420 kV. So this already we have done 420 kV, then it is not absorbing, it is supplying to the grid 39.7 MVAR. Now let us suppose the system is operating at night time when the connected load to the grid is lower, then the transmission line shunt capacitors also injecting the reactive power into the grid. Due to that reason, the receiving end bus voltage may increase from 100 to 102%. Then to maintain the 100% generator bus voltage, the generator needs to inject only 20.6 MVAR. Only 20.6 MVAR they need to generate. To maintain the 100% generator voltage, bus voltage, the generator needs to inject only 20.6 MVAR, as already we have seen. Now, let us suppose the receiving end bus voltage increase to 105% or 105%. In that case, again, like we can take, can copy another case. So select the entire, then Control C, and then move from temperature. Go to the edit mode. Control C, move from temperature. And my case 3, grid voltage now change to 105%. Click OK. And then here also we have to go rating. Here I need to change to the 105 from 102. Click OK. And then again run the load flow. So here now when it is changed from 102 to 105%, then you see, in order to maintain the terminal output voltage as 100%, now what the reactor operation is changed. The generator performance is changed. Now generator has to absorb 0.79 MVAR or 7.9 MVAR from the grid in order to maintain the output voltage as 100%. 0.79 MVAR, as you can see over here. Same thing we have mentioned here. So let us suppose the reactive power receiving in bus voltage increased to 105%. Then to maintain the 100% generator bus voltage, the generator needs to absorb 7.89 MVAR because it is with the negative sign. It means it is taking from the grid, absorbing from the grid. So we can say that the daytime, the generator is operating in the overexcitation range. In the daytime, generator is operating in overexcitation range, overexcitation range over here, overexcitation range over here. Based on the capability curve, again, you can correlate this overexcitation range. And in the night time, overexcitation range, and in the night time the generator is operating in underexcitation range, and they are consuming this 0.789 MVAR from the grid. So I hope this is now is it clear how to model the generator for the load flow analysis purpose, for the short circuit analysis purpose? Is that clear? This generator, first info page, swing, voltage control, MVAR control, power factor control. So voltage control mode, then go to the rating. Here we have to define the rating. Plus we have to define the Qmax and Qmin limit, and how to calculate the Qmax and Qmin limit. I hope this is clear to everyone. And based on this, we have done some case study as well. Is this both value is clear how to calculate?
Yes, sir. Clear.
First of all, we get the capability curve, and from that we enter the value. But in case the generator manufacturer capability curve is not provided, and most of the time they hesitate to provide, or they do not provide in first submission. In that case, in order to model with help of the power factor PF, we can also find the Qmax and Qmin value, and that we can mention over here. And then we have seen a small brief about the capability curve. And then after we have impedance per model. So this, if we require further, then we will model it. Okay, so transient equivalent. But for the load flow analysis, this type is this much is required. Capability curve, this we have done. This we will see the impedance modeling further for the other calculations. Then grounding, like we take like star and solid grounding or NGR if required, so we can connect with the NGR as well, register as well. Based on the SLD, we can change this. Then inertia, exciter, governor. So governor here, I think we can take any type of the generator, synchronous generator. Let us take steam turbine ST type. So here we have mode, droop mode and isosynchronous mode. So two mode also available, droop and isosynchronous. Let us see what is the meaning of droop and what is the meaning of isosynchronous. This meaning. So governor control mode along with the generator operation mode. The generator governor has two type of the control mode. One is the droop mode and second is the isosynchronous mode, as we can see over here. Droop mode and isosynchronous mode. Governor control mode, droop mode, they are used for load sharing among multiple generators. Frequency varies slightly with load changes, and so when we have multiple generators, and among that we need to share the load, then we take the governor in the droop mode. And isosynchronous mode, typically used for single or isolated generator system operation. In that case, we go with the isosynchronous mode. Frequency kept constant regardless of the load changes. So in large power system, large power plant, droop mode is commonly used to ensure a stable operation with multiple generators, while the isosynchronous mode is more typical or more common in stand-alone or critical applications where the frequency control is vital. The generator is running in an island operations. In that case, the isosynchronous mode of the generator governor we select. This is a brief intro about the governor control mode. Okay, so that's all about the generator modeling with respect to the load flow analysis and with respect to the short circuit analysis as well. So am I clear with this rating, how to define the generator?
Sir, Raghav
Sir,
sir,
can we put
Yeah, yes.
sir, how we can put the Q minimum and Q max value by seeing capability curve?
Again, in the capability curve, you see here, so in the capability curve, you will get this kind of the curve, right? Again, so
Okay,
in
sir.
the capability curve, the Qmax and Qmin value given. Could you see here? It is a capability curve. Example of a capability curve of the generator.
Okay, sir.
It is semicircle curve. What is the transformer capability curve? Anyway, so you can see over here in this capability curve, you can see Qmax here.
Yes, sir.
So this is your Qmax limit in the ETAP. Under Qmax column, you have to put this limit, this value. Here I have put Qmax, but this value they will provide the generator manufacturer. The limit,
Okay.
the value they will provide over here. Okay.
Okay, sir. Okay.
And similarly,
Sir, it's not provide.
yeah. And similarly here, the Q minimum, this limit value they will provide over here. So that Q minimum with negative sign we can put over here.
Sir, in a generator, how we are measuring the absorption of reactive power, sir? Is there any particular method, sir?
Particular method means you need to like take your different generator loading conditions like here we have done, and then with help of the ETAP, then you can calculate how much the active power or reactive power they are generating, they are importing or exporting to the grid. The different scenario you can see over here.
Yes, sir. For that, we require bus voltage and receiving end voltages, and we can simulate in the ETAP, and
Yeah.
we can
Yes.
find it. Yes.
Yeah, we can find it. Yeah. So like that, you can make one network, the generator on which it is connected. So
Yes.
then you can run the load flow, and then you can see how much reactive power they are injecting or they are absorbing.
Okay, sir. Thank you, sir.
Yeah. So with negative sign means they are absorbing. Okay.
Yes, sir. Yes, sir. Negative
If
sign
no
is
negative
absorbing.
sign, it means they are providing,
Sir,
injecting.
in the case 3, the generator bus terminal voltage is varying, sir.
It is 100%.
This is 100%.
Yeah. So
In
they
order
want
to keep
generator
this
wanted to
terminal
keep.
voltage
Yeah.
constant, we are
Yeah.
yeah.
Yes, generator want to keep the terminal voltage constant, and accordingly the reactive power they have Qmax and Q minimum limit. Accordingly, they will adjust this, the maximum and minimum reactive power, adjusting to this constant bus voltage.
It was originally because of the receiving end voltage is high.
Yes, hi.
Yes, sir. Thank you, sir.
Yes. Okay, so that's all for the generator for my load flow analysis purpose or short circuit analysis purpose. Okay, now let us go with the next equipment, which is the transformer. So this generator,
Sorry, sir, interrupt you. In generator, we have required a inertia value, recitation value.
generally for load flow analysis, there is no need to mention over here.
But if we calculate short circuit,
No, that also not required. For here, inertia value, right? No, that no.
yeah.
For short circuit also it
Sir,
is.
can you little bit explain how we can put these value in this portion? Is it possible to explain this one?
As you here we have prime mover, here coupling, here you have generator, so then inertia. So generally this we can ask from the generator manufacturer as well, like inertia, RPM is your like rotator speed here, then WR square H. So H is your inertia, like that you can mention over here. So generally this value we ask from the grid, and if you want, once you install the ETAP, then you go to here help menu. You can also see their meaning. Otherwise, if time allow, I will also pick up this point and I will also take up. But otherwise, if you want, you can go through this inertia calculator as well. Here, prime mover, coupling, and generator RPM, WR square, and H. So they have also mentioned RPM, WH, arithmetic sum of the prime mover, coupling, and generator H in megawatt. So soft torsion,
Okay.
torsion. So this also you can go through.
Okay,
But
sir. Thank you.
generally, for load flow, no need to mention anything over here about this.
Sir, which kind of calculation we require these values? Let's suppose if we have
For short circuit also it
bit,
is not required. I don't think for load flow, short circuit, relay coordinations, it is not required. Might be few transient study. This could be, but I have not entered here. I have not used here. Uh, this is a options available. If required, we can ask the manufacturer. We can put the data over here.
okay, sir, for harmonics, if any requirement of harmonics,
No, for harmonics also not. It is not required.
but generally we have used harmonic calculation.
Mm-hmm. For
Let's
the
suppose we have
harmonic,
a generator.
for the harmonic calculations, have you entered all those values?
No, no, sir, for, harmonic portion. Can you please open the harmonic portion? Basically, in ETAP, we also calculate the harmonics of equipments, no, sir?
Yeah,
So
yeah.
when we calculate the, yeah, for harmonics, we also required harmonics for a generator also. What is the generator harmonics? Transformer harmonics.
Mm-hmm. Yeah, yeah, yes.
So can you cover harmonics topic in this ETAP calculation?
Okay, I will try to cover the harmonics analysis as well. It
Sir,
is not part
basically
of the
ETAP, two or three topics are very important. One is harmonic calculation, one is load flow and short circuit is a normal, then arc flash calculation, relay coordination.
We are
These are
covering,
very important topics.
we are covering the relay coordinations. We are covering the load flow, short circuit. For harmonics, I will try to cover if time allowed, and for the arc flash as well. Otherwise, I have covered in one of my previous batch. That recording video also I can upload it. You can.
Yeah, no problem. If you have a recording, please upload. We can
Yeah, yeah, I will.
review, see, and obviously we will. Basically, this portion is a weak from us, na. For my side, this portion is weak from my side. For load flow analysis, for a short analysis, I will calculate it. Also, relay coordination little bit. Motor acceleration is also topic. So, is it possible, please calculate harmonics and then arc flash, and third topic is motor starting.
Yeah, okay. Yeah, no one, okay.
Thank you, sir. Thank you, sir. Thank you.
So, and anyway, so far, Noman, I'm clear. I have whatever I have done the first ETAP introduction, and thereafter
Yes,
we
sir.
start the equipment modeling, and then we discuss the bus bar modeling. Then we started with the source modeling, and for the source modeling, we pick up the grid modeling, and after the grid, we took one conventional generator and their modeling we have done so far. Okay, so so far I'm clear with you. Each and everything is clear, Noman.
Yes, sir. It's clear, sir. It's clear.
Okay, so I think you can, so far you can practice as well with you as well. So let us go with the, since this generators and this grid is connected with the transformer. So let us do a transform modeling. So for that, again, select, drag and drop the transformer. Click on here again, first info page. So put the ID on which bus it is connected. So primary, secondary bus we can select from here. So it will automatically connect to both of the buses. Standard IC or NC that we need to select over here. Equipment tag, name, description, service in conditions, 3-phase, single phase, cell type or port type, whatever. So that we can define over here. Then go to the rating page. In the rating page, my transformer, primary voltage, secondary voltage, and then MVA you need to mention here. And then alert maximum B, that also we can mention here. And then altitude installations above sea level. So altitude generally in ETA by default is coming 1000 meter, but if you want to, we can increase this altitude. If we increase this altitude, in that case, my my transformer, the rating will start. You can see the 100 MVA transformer now directed to 96 MVA, and there's 4% rating. So every 100 meter provide 2% rating. So this we can mention ambient temperature where transformer going to install that we can mention over here. And then temperature rise, class, cooling of the transformers, cooling type, class of the insulating oil, so that we can select over here. Liquid, fluid or dry type, that we can select over here. This is the rating page of the transformer. Thereafter we impedance. So for impedance, ETAP, since ETAP is linked with the IC60076, so ETAP will automatically take the typical impedance based on the transformer MVA power. But this this impedance, whatever ETAP is taking, this is not as per the updated IEC version. It is based on the old IEC version. So we need to double check whether whatever the percentage impedance they are taking, whether it is accurate or not accurate, correct or not correct. And if it is not correct, so we need to provide the impedance over here. So here we can model.
Sir, normally ETAP is calculated in correct values.
Yeah. So if ETAP is taking as per the correct MVA, then it is fine. And if not, so based on that transformer manufacturer, positive and negative zero sequence impedance, we can put over here as well. And the next YR value also we can, like, ETAP will automatically take, otherwise from the transformer data set we can mention over here. Then tapping, we'll take the tapping in a separate class, how to about the tapping. So here we have the two tapping. The fixed tapping means it is my OCTC, off circuit tap changer. It is fixed type. So here we can primary and secondary. Like here we can provide the tapping range. It is my fixed tapping, OCTC tapping, and then we have the on-load tap changer or OLTC. So in the OLTC we have to select this option, and generally we provide the OLTC on the primary side or HV side. So and this to regulate the voltage or to operate this OLTC, we have the AVR panel. So we have to select that where OLTC going to place. Generally it is on the primary side. So AVR we have to select over here, and then here we have to mention the this LTC OLTC range, maximum minimum range we have to select. So this we will do later on. This we will do this modeling. But this modeling we will do along with the load flow analysis, this tap changer, because what the tap setting required, that value we will know based on the load flow analysis result. So this, but here we have the option, we can do this. We will do this in next week, along with the load flow analysis, the transfer tap changer selections, that we will do this. Then grounding of the transformer, here we have the primary, secondary, star, delta, whatever we want, we can set, like change from here. If you wanted to show the symbol, so we can click on the symbol, so it will appear. Then like sizing, generally no need to put anything over here. Then we have the protections. This is important, this one for the relay coordination purpose. This is my thermal curve of the damage curve of the transformer. So this taking this damage curve, when we do the relay settings, we also consider this curve as well. And all the relay settings should be below this damage curve, because on this damage curve my transformer will be damaged. So all my relays should operate before this curve. So this all we will set when we will come on the relay coordinations. So we will coordinate the relay curve with this transformer damage curve. So this option we will see during the relay coordination topic, and here we will select the values. Okay, and here we have the harmonics. So at the time of the harmonics, this we can utilize this page as well. Okay, so these are some typical settings for the transformer modeling. So ID, enter a unique ID with 25 maximum 25 limit, condition service in, then tag, name, description, that all we can mention there. And then voltage rating, primary, secondary, we need to mention. Bus kilovoltage nominal, we need to mention. Power, or otherwise when we connect to the bus, it will automatically show the bus kV. Power rating in the MVA or kV, there we need to mention. The rating MVA, this display the rated MVA for each class. Our temperature rise and the installation, the altitude height. Subtype, fan or pump, that we need to select from the subtype. Okay. And then we have the transfer expire ratio. So generally we are taking this from the data sheet, but otherwise we can also calculate it. ETA will automatically calculate, but if you want, we can also calculate it. We can also verify it whether this calculation is correct or not. So in order to find the transfer expire calculations, the transfer expire ratio measure the ratio of the transformer inductive reactance to the resistance of the transformer winding And below input required before the calculation of transformer X by R ratio. So we need the GTP of the transformer, RFID report of the transformer, or the datasheet of the transformer. And in that datasheet, we can see what is my copper loss in kilowatt. Through that datasheet, we can get the copper loss of the transformer. And then we need to know about the percentage impedance of the transformer, and then rating of the transformer. And then we can use the formula, because X by R I need to calculate. So I can calculate the R. So R, to find out the R of the transformer, the formula would be copper loss in kilowatt, divided by the, so copper loss would be your full load loss, right? Isn't it? What is the copper loss? It is load loss.
So your screen is not visible, sir.
So screen not is it is not visible.
Now, okay.
Yes, now okay.
Yes, sir, it's okay, sir.
It's still not visible. Yeah, it's okay, sir.
Yeah, okay. So in order to find the transfer X by R ratio, we can take this formula. So the R would be copper loss of the transformer divided by the MVA rating of the transformer. So let us take one example, and then once we know the R, we know the impedance, then we can find out the X. So easily we can find out the X by R of the transformer. Let us see with one example. So let us take one transformer with the, let me take the snapshot of this transformer X by R ratio calculations. Usually the ETAP will suggest this X by R ratio directly, but if we want, we can also calculate it, or we can see that how that this calculate. So let us see that transformer rated power is 2.5 MVA transformer, and my primary site data set take a transformer which is 2.5 MVA and 11 by 0.433 kV. Okay, and let us take the transformer full load loss which we get from the transformer data sheet, or technical data sheet, which is 17.9 watt, 17.9 kilowatt. And let us take the transformer percentage impedance of 2.5 MVA is 6%. So first of all, what we do, we calculate the R. So R would be the copper loss divided by MVA rating. So my copper loss is 17.9 kilowatt divided by MVA, which is 2.5 MVA. This rating is in the kilowatts. So due to that, doesn't convert MVA into KVA. So 2.5 into 1000, that would be your resistance R. Convert this into percentage, because we wanted to know that percentage R if we want. So we can multiply it by 100. So we get the percentage R, 0.016%. So we know that impedance, which is 6%. So to calculate the percentage X using the impedance triangle formula. So my impedance triangle means my Z here, R here, X here. So Z would be square root of X square plus R square. Right. So we know the Z, we know the R, so we can find out the X. In that case, like Z square would be, so my X would be, so Z square, if you take a square, so that would be X square plus R square. So in that case, my R would be Z square minus X square, R square. So R would be square root of Z square minus X square. So Z square, in that case 6 square minus R square 0.716 square, right? So we get the percentage of the X. So my X by R would be this X we know, X 5.97957 divided by 0.716. So my X by R would be 8.3199, which is same for both rating of the transformer for the HV side and for the LV side. 8.3199. So again, we can take any like rating, take any 2.5 MVA transformer. Let us go with 1000 meter altitude. Okay, percentage impedance, let us go typical. Now it is 6.25. So you can see, since it is 6.25, not the 6%, so X we are coming over here as 6, right? Isn't it? Same, like we convert 8 because in my case Z was the 6%. So due to that reason. So if we convert this as 6%, then let us see how much it is coming. Percentage X 5918, percentage X 5.9571, and then R 0.986, R with 0.986, R 0.716 here coming. So accordingly X by R it is again coming 6. So we need to enter here as 8 now because it is coming 8 here. So here we have to enter 8.311. So in that case, I will not go with the typical data. I will go with the exact data. 6% here impedance, and X by R we need to change at 8. What we calculated over here. Okay. Not the
There
typical.
are another simulation software which is a bit silent, I think. He can calculate accurate.
Yeah, we can. So either here also, if it is not telling the exact value, so we can calculate like this, and then we can enter there in the ETAP. Okay, so let us see one other equipment modeling. So this is about the transformer modeling. Okay, it is very straightforward, nothing straightforward transformer modeling. Now this generator connected with the transformer. So transformer modeling we have seen, grid modeling we have seen. So between when we connect the generator to the grid through the transformer, then we have the transmission line as well. So let us see the transmission line modeling. So go here. So here this option it is telling the cable, and this option you can see this is overhead line. So in the overhead line, you can see that we have the like overhead towers, and then on that overhead tower there we have done the swinging of the conductor or hanging the conductor. So it is, you see here, it is also in the transmission line, it is like conductor swinging, it is also swinging. So directly you can see that this symbol, it is representing the transmission line. Just drag and drop over here and then click here, and then here first info page, info equipment IT service in conditions, then you can see here, and then here we define here that what is my transmission line length. So this value we define over here like 50 meter, 100 meter or whatever, and then unit of this length, whether in the kilometer or in the meter, mile, foot, so that we defined here. Okay, then after that we go into the parameters, and here in the parameters we can ETAP is have inbuilt library. So from that inbuilt library we can take the defined or the required conductor type, whatever the required conductor type we can select over here, and then whatever the conductor type is selected, based on that library, the resistance R value, X value, ETAP is automatically suggesting. So either we can go with this parameters. Otherwise, if we don't want to go, we have our own project specific parameters. In that case, no need to select any library conductor over here, no need to select over here. Directly go to your impedance, and here you can define your conductor parameters like resistance, then R, X, reactance, and Y susceptance. Here we can directly define over here, positive, negative, 0, that we can define over here. Then we have configurations by transmission line tower height. So this we can define over here. And then spacing ABC, it is RYB phase. So A to B is spacing like R to Y spacing. So as per the transmission line tower diagram, we can enter the value over here. A to B, RB, and B to C spacing. That and CA this will automatically take. If we wanted to ground wire, so we can define the ground wire here as well. And if there is transposing happens, this transposing also we can select, and then we can define that what is my separation distance and one conductor per phase, how much we have. So that also we can define over here. So here we can define their other configurations related data of the transmission line. Okay. So transmission line. So before modeling, let us see the parameters. What is the meaning of R? What is the meaning of X? And what is the meaning of the this Y substance? What is the meaning of those parameters? So the transmission line can be modeled either in the nominal pi mode or the nominal T mode. These two options we have, and this is our basic electrical engineering as we have studied in the college time as well. Nominal pi and nominal T model. Nominal T model, this is the series impedance. So in the transmission line we have series impedance, right? And then shunt capacitance. So the series impedance is divided into two equal part of whatever length we have. So equally we divide into two equal part, and the whole shunt capacitance and admittance of the line is assumed to be lumped at the middle of the line, as you can see over here. The whole if this impedance and this impedance clubbed together when modeling, and then this total shunt like capacitance and admittance is lumped in the center. This is the T model type representation of the transmission line. Whereas for the pi model, the series impedance of the line is concentrated at the center, and the shunt capacitance of each line. Shunt capacitance means phase to neutral is divided. Shunt capacitance is divided into two equal part. It is divided. One part is lumped at the sending end, while the other part is lumped. Lumped means jointly we are taking one value, are collected. Lumped at the receiving end, as shown in figure. In the ETAP for the load flow study, the transmission line is most of the time modeled in the nominal pi model. For the transmission line modeling, we need to enter the resistance R. As you can see here, we need to enter the resistance R here. So we have two resistance like R at temperature T1 or R at temperature T2. So because when my resistance, when my conductor temperature is increasing, due to that the conductor resistance is also increasing. So like one temperature we take at the base temperature 20 degrees Celsius, and then we take what is my conductor operating temperature like 75, 85 or 95. So based on that we get some different resistance value, and that we need to put over here as well. Okay, and this value we can ask from the manufacturer as well, that if 20 degrees Celsius, so what is the temperature? If 95 or 85, so what is my resistance of the conductor? So they will provide, and then we can put over here. This my ETAP is my old version. Due to that reason, this second RT2 is not showing here, but in the latest version like 19, 18, 20, the RT2 will also show over here. Okay, so resistance, then we have to enter the reactance value, X value. We have to enter the X value in the ETAP, and the susceptance Y, where the Y is the combination of the G and JB, where G is the shunt conductance, and B is the shunt capacitance. G can be neglected, shunt conductance, because no any conductive path over here, no current is flowing here, so the shunt conductance would be very negligible. So due to that reason we can neglect this conductance, and only the we have the shunt capacitance. So G plus JB only, it can be, G can be neglected, so Y can be as B also. Y susceptance can be B also, and B is my shunt capacitance. So that we need to enter in the transmission line model as well. So drag it from this equipment, double click on it, then mention the length and line parameter, impedance of the line, and for parameter two options available. We can select from the library, as already we have seen. For the parameters we can select from the library. from the default library of the transmission line. This one option. Second option, we can select from the inbuilt library. The line configurations is important to define, or we can put it manually by selecting the user defined option in ETAP. And for that, whatever your project informations you have, for that go in the impedance, and here do not click on the calculator, click on the user defined. So once you click on user defined, then this value here you have the choice, you can define yourself here. This value you can edit here, you can edit over here. Then you can see here RT2 also coming, RT2 that we need to mention, and X and Y value we need to mention. So R, X and Y, this value we need to mention, click user defined. So typically, for example, our resistance of 0.1 ohm per kilometer, let us suppose at both T1 and T2 temperatures, that we can mention there. X would be XL, and that would be 2 by FL. It is my reactance. So generally, this value, in absence of any value, we can take 0.4 ohm per kilometer. So the X value we can go with 0.4 ohm. Otherwise, we can ask manufacturer to provide this value. So 0.4 ohm, the value of the X. And admittance, which is susceptance or admittance Y, that G plus JB, G is neglected, so Y is equals to B, which is 2 by FC, which is, we can take as, for example, 3.6 microsiemens per kilometer. Again, this value we ask from the client to provide, and that value we mention here. And all static equipment, positive sequence value is equal to negative sequence value, and zero sequence value is approximately 3 times the positive sequence value. So whatever we are putting here, same things we have to put in the positive sequence, same equal to negative sequence, and in the zero sequence we can multiply 3, and same value of the positive sequence we can mention under the zero sequence as well. Okay, so for the ETAP modeling, this parameters we need to know. This parameter we need to know. Okay, so we discuss for the load generator modeling what parameter we required. We required the ratings, and we require the Qmax and Qminimum. Then we discuss about the grid, what parameter we required. Then we discuss for the transformer what parameters we required. So we need to know the transformer ratings, their impedance, and their OLTC range. So all, and this value we get from the rating data set of the transformer as well. Okay, so what I have done here, so just for the other equipment modeling, you have to drag and drop, and you need to enter the input required value. So I have prepared one list that you can refer for all equipment modeling. So if you see here, for the equipment over here, their name, and for load flow analysis, what the input we have, V minimum required. For the short circuit analysis, what value V minimum required. For the generator, like voltage, VQ, active power, then power factor, Q minimum, Q maximum, grounding, compound excitation details. This will required for relay coordinations, what required. And you see transient stability, as I mentioned earlier, Numan. Here inertia you can mention here for the transient analysis purpose, inertia.
Okay, sir.
Okay, and for harmonic analysis purpose, generator should be MVR control mode. Nothing, no any input you require, no any inertia, just generator you need to switch into MVR control mode for the harmonic analysis.
Okay.
For motor exertion study, nothing, grounding compound and excitation details, and for arc flash study, nothing, same voltage, power, reactive power, power factor, Qmin, Q maximum, and type of the grounding. So for the generator, similarly, like you drag and drop, and you see that what the study you are doing, and for that study, this input you have to ask from your client. This is input required before doing any study. Before load flow analysis, you need to know the grid voltage are just voltage enough. For bus voltage is enough. Generator, you need to know mode of operations, that voltage control mode, voltage, the reactive power, active power, and power factor. That's all you require when you can run the load flow for the generator. And Qmax and Qminimum, you have, I mentioned Q. So if you know Qmax, Q minimum, you can ask. Otherwise, from the power factor, you can calculate the Qmax and Q minimum. For the transformer, this input we required. For the breaker, for the load flow breaker, no need to mention anything, not mandatory. For motor, kVA voltage, power factor, rated current. The static load and lump load standard IEEE 3002 or IEEE 399 we refer for the load flow analysis purpose. So for each analysis purpose, for the equipment, what the input required, I have listed over here. So you can take reference of this inputs, then go to the ETAP, drag and drop the equipment, double click, and then editor block will open, and then you can enter those values. And thereafter, you see that what study you need to run, and then you can select the study and you can run the study. Okay, so let us run the load flow analysis study. And for load flow analysis, how to model the load, how to select the transformer tap settings, and how to model how to mitigate if excessive reactive power is coming. So how to mitigate those reactive power, or how to select the capacitor bank. So let us see all those things. So it is okay to start now or in the next class?
The next
I
class will
think
be
we can
better.
start in next class.
Okay, so I will provide this presentation.
Raghav, 1 to 2 questions. Uh,
Yeah, hello. Yeah, Somajit.
1 to 2 question is for I am modeling today one ETAP that everything is inside of that switchyard. For cable purpose, do we consider any setting or not required?
Say again, sir. Say again.
Breaker to transformer, suppose 2 MVA transformer, there is a 50 to 20 or maybe 70-meter cables. So these cable are to be considered or not?
No, you need to consider, sir.
Okay.
Yeah.
And another thing is, please go that generator capability curve.
Yeah.
And
Okay.
this is a QC and QD you have set in 60 and 20. That was not clear to me.
No, I have not set like 60 and 20. I'll go there. Go there. Capability curve here.
Yes.
So, sir, P
Q.
minimum is the minimum reactive power that generator need to deliver, sir. P minimum,
Okay.
minimum reactive power, minimum active power, minimum real power, megawatt power.
Okay.
So
So
that,
from where this value is coming?
sir, this value we have to ask from the generator, because
Okay.
it is the generator capability. How much generator capable to deliver? But here I took just one value for an example only. Here, and the QD value, sir, this QD value we take generally near to 2 times of the QC value here. But again this QD value we ask from the generator manufacturer, because this is their own equipment capability. So they need to tell their capability.
Okay.
Yes, sir. So here you
Okay.
see.
Thank you.
Yeah. Okay, I will upload this recording, video, PPT. Have a look, and if any doubt, we can discuss in the next class as well. Okay, Somajit sir.
Okay. Thank you.
Okay, so for Wednesday, I will try to keep the transmission line model if keep as available. If not, then might be I can take one class on Wednesday or Friday for the next equipment. Or if not, so we have on the weekend, next weekend on Saturday. I will update.
Sir, another thing, when we put a labeling of equipment, can you open your slide, which you have mentioned a E-type modeling?
Labeling of the which slide, Numan? Which page?
Sir, I not remember you, in which you have draw
I
whole
think he is
transformer,
telling about
then there's
altitude.
Yeah, sir,
Okay.
this one. Sir, ये ID, KV, how we can label this value?
Oh, here you just display, na?
Yes, sir. How we can display?
No, you display go here, and whatever you want, you can display here.
No, sir. Basically, this when we calculate, then we can show the display, na. But these value can show here for a permanently. Let's suppose if we take a report, all of this value show here. In
So
any
in
equipment, let's suppose if we mention in a transformer, we have mentioned the transformer rating, transformer. Let's suppose we have mentioned vector group, everything we have mentioned here in a separate red form of label red form. How we can mention here?
So for that, see one option here, display option. I think which version ETAP you are using, I'm not sure. Otherwise, you right click here, and then this is my old version. It is not coming here. Otherwise, here we also get. Then you also show here on the right click. I'm not getting because I'm using very old version. Then here also you get that. You can show ID here. ID about the
Okay, in
equipment.
this, okay.
So by
In
right
this
click.
question, we put all the data.
Yeah, whatever data you have put, so first model this and then right click and then you can show the ID. And this is one way without doing any analysis. And once you have done the analysis, in that case, you have the second options. You go under display option because when we submit the reports, so we generally submit the report after doing the analysis. Numan.
Yes,
So in
sir.
that case, we have the options like what we wanted. So generator, their KV, grid KV. So all these things, motor, bus ratings. So that all you can click from here, and then you can show there. I have my old version, so I do not have. Otherwise, there is two column more here, so you can show in that during that condition as well. Transformer trap, DY. You can show here.
Sir, uh,
Yes, sir.
I
Thank you.
had
Is
installed
there
that.
anything, if we print the report, can you please give example to print a report?
Yeah. So when we have not done any analysis here. So once we done the analysis like load flow analysis or anything, then you can like report manager, you can generate a report. Or once we do the next class, then we'll generate the report as well. Or here also you have the options, then you can generate the report. In my system, it is slow, but here you have the options. You can generate the report. So here you have the options,
Sir,
report managers and analysis report analysis. So from here you can do, or here you have the options. And you can also generate the report.
Yes, sir. Understand. Sir, is it possible that we can paste this picture and on a report?
Yes, you can paste this picture. I think the report also it will come. Otherwise, you can like paste this picture as
Generally, basically, my concern is that in generally, when we can generate the report, ETAP single line diagram is not shown in this portion.
well. Yeah, in that case,
So
you can paste there.
you can take the screenshot.
The screenshot you can take and then you can paste there as well.
okay, sir, thank you.
Sir, I was having trouble with the software activating. I've already installed it, but not able to activate.
Not having to activate.
Uh,
What is it?
Basically, if you want to active, you can download from which website?
Get into PC.
Okay, first you can download your software, then turn off your firewall, internet, then start installation. After complete the installation, you can open the crack file. Just copy the crack file and install on a that file folder which you have installed a ETAP. So after installation, you can paste a crack file. Then he can, I think he can give option to replace this. Then press yes, and then close all the system, and then right click on ETAP file and then run as administration. So you can start this portion. So if you install one time, completely delete it, then install it again.
Okay.
So transmission line modeling is quite complicated, sir.
Yeah,
Like parameter setting is quite complicated.
yeah, okay. Like
We can see it again in next class, sir.
see, in the transmission line modeling, Bimal, we do not have because most of the data is we take from the user, from the client. So the first is my info page. This is okay, Bimal.
Yes, sir. Yes,
Then
that's
you go
okay,
to the
sir.
parameter. Here you have that by default conductor type. You can select from here. You can choose from here. This is option 1
Sir,
for
sir,
the.
we could not find the conductor that we use in our real project, sir. Why is that, sir?
So for that, you go to the impedance here and click on user defined, and then put all your conductor data over here,
Okay, sir.
because you will get the resistance, reactance, and susceptance of the conductor, transmission line conductors.
Okay.
So that we need to enter over here, and the length. Length first, second parameters. Two options we can select from library. Otherwise, from conductor and from the grounding as well. Otherwise, no need. And if we are using this option, then we have to go to configurations, and here we have to define the conductor transmission line height or conductor height, and conductor phase-to-phase spacing. We have to define it. This is option 1. Second option, no need to do anything. If you working for any project specific, then directly go to the impedance tab, and here you put your impedance, select user defined, and then put here your positive sequence resistance at temperature T1 and temperature T2, and then your reactance, and then your susceptance. And this value we ask from the client to provide this about the conductor parameters. And in absence of those parameters, for the practice purpose, like as we discussed, like 0.1, 0.4, and 3.6, that generally we take, and then we can have one practice. And if one working for the real-time project, then this parameters we ask from the client to provide, and same parameter we enter over here. Okay, Bimal.
Okay, sir. Okay. Thank you, sir.
And we have our own database in this for conductor, like Zebra, whatever we normally use.
Yeah, so for that, this is your database. This is your
No, but
database.
now we have to, every time we have to put, no, can we save it or store it?
What happened when we work for any company, that company, whatever the project they do, so those database, they also have defined in the library. So in that case, like you have to like make some additional library, and then whatever the data the conductor you are taking, so that conductor data set you have to create that library in that case.
So can we create the library, our own library?
Yeah, yes, we can create. Yes, if time permit, I will try to take up this as well.
Okay.
Library creation as well. Okay. But generally, whatever when we work for the company, they have, because they are not doing first time, they have done multiple projects, so they have the library for Jabra, Moose, or whatever the popular parameters we have. So we select those, and we do the load flow. Okay, anything else, any doubt, any query? So I hope that you all learned the generator modeling in the for the load flow analysis, for the short circuit analysis, right? So what is our key takeaway? Could anyone like summarize today's session? What are key takeaway? What we learned today? What is our key learning today?
Generator modeling.
Yeah, so we discussed about the generator modeling. And in the generator modeling, we discuss about the Qmax. What is the meaning of Qmax? And what is the meaning of Qminimum? And how? So first we understood the basic concept about the Qmax and Qminimum. And thereafter, understanding the basic concept, we discuss how to calculate the Qmax and Qminimum in the ETAP with help of the power factor, right?
Yes.
So how to find out the Qmax with help of the minimum power factor? With help of minimum power factor, right? This value gives the Q maximum, and for the Q minimum, with help of the
Max PF.
maximum power factor, so that we get the Q max and Q minimum. So this value we copy and then we enter into the Q max and Q minimum column. Q max and Q minimum column we pencil, and for that, in the like operations, we have to take this in the power factor control mode, PF control mode, to get this value. So we discuss about the generator modeling, Qmax and Q minimum. Little bit we discuss about the briefly about the capability curve. Then we discuss to draw this capability curve in ETAP as well. Otherwise, we take this curve from the particular generator manufacturer capability curve, right? Then we discuss briefly, not in detail, about the governor mode, right? Briefly, and thereafter we discuss about the transformer modeling. In the transformer modeling, like it was straightforward, and because multiple time we have done this modeling. So, but today we discuss about the transformer X/R ratio calculation as well. Again, it is very straightforward formula. Okay, so transformer, and thereafter we discuss about the transmission line modeling. And in the transmission line modeling, we discuss that we have the two options. First of all, we have to define the conductor length, and then when it go to the parameters selections, then we have the two options. We can take one the by default conductor library. From that we can select any specific conductor, and for that we done the load modeling. Or otherwise we can go with the parameters tab directly and click on the user defined, select this value user defined, and then we need to define all my conductor resistance, reactance, and susceptance value. Positive same with the negative, positive negative same for static equipment, and then zero sequence. The zero sequence value would be 3 times of the positive value. So if I'm putting 0.1, so I will put here 0.3. Some typical value I have like defined, I have like mentioned in the PPT as well, so that also you can refer, and then you can model this. So thereafter we discuss that this is input we require. So we discuss that what the input required for different type of the equipment, for different type of the system studies. So one page for overall input required for the equipment modeling. So that page also you can refer with respect to the different type of the system studies, right? So this we can take this snapshot of this page. This would be useful. Okay, this would be useful for the to know that what the input we require for different type of the system studies. Okay, so that's all we discussed. So let us so we discuss the introduction of ETAP. We discuss how to model the equipment and what the input we require, and some equipment we have also modeled taking the input. And for other equipment, we listed here what the input required. So just take this input, then drag and drop the equipment and do the modeling of the equipment. And now we will go to the analysis. So first we'll start the load flow analysis. So taking now the equipment model already we have done. So just model the equipment and then run the analysis. So we'll run the analysis, and for that we will do the load modeling for the load flow analysis. So for the load modeling, we have not done the load modeling under the equipment model because we will pick up this um, load modeling under the load flow analysis purpose. So type of the load, like we have the constant power, constant current, constant impedance type of the load. So those load and the example of those type of the load and their modeling. And after the modeling, then we will run the analysis, and then we will see what is my real power flow and reactive power flow, and then accordingly how to mitigate reactive power flow. So how to improve the reactive power flow, how to improve the power factor, how to adjust the transformer tap settings. So that all we will discuss in the load flow analysis topic by next week.
Some modeling of circuit breaker and CTPT.
That's very easy. Yeah, that's very easy. No need to do here. Just take the breaker. You have option that breaker here, right?
Okay.
I think breaker modeling already we have done. Just drag and drop here. Then go here, status open or close. First of all, your breaker status. Then go to the
Okay.
rating. And here in the breaker topic, I have discussed already all those things.
Okay, sir.
First pole to clear factor 1.3, 1.5, ITHR, TKR. This all we have discussed in the module number 2.
That I can refer from the module
Yes.
module 2, I think.
Yes,
2.
yes. Making
Okay.
peak time delay, rated kV, rated ampere. This all we have discussed. Okay.
Okay, sir.
And then again you can take the CT, just drag and drop over here. CT mod, double click over here. Then rate CT primary current, secondary current. That's it. And then
it's a simple one, I think.
Yeah, simple. Then designations. For metering class, we do not have any CT. We have CT in the ETAP for the protection class only. We do not have any metering class CT. So designation 5 to 20 or whatever my protection class that we need to define over here. That's burden of the CT. That already we calculated 10 BA, 5 BA, so that all we need to define over here. Okay. This CT calculations already we have done. The ratio calculations that we need to enter over here.
The version you have shared, 2020 of ETAP, is this the only version available in the market, or the latest version is?
No. Many other version also available. This version was easily available, so that's why it's there. Other version.
Okay.
Okay. Yeah, Amit, I have seen your message. I will arrange. If actually I'm suffering from time not getting the time, once I get the time, I will try to arrange it. If anyone have, they can say to Amit some layout they are asking.
Amit Patil ne message kiya. Okay, sir. Sir, I have also prepared one, SLD on ETAP, that 7.5 gigawatt. If you remember, I was talking with. So can I share that also, and if you can check?
Yeah, okay, maybe. Okay. Say I will try to check.
Okay, sir. Okay.
Okay, so
okay, sir.
I'm not here. Amit not here. Yeah.
Sir,
this is I cannot download 75 gigawatt. Oh my god, I do not have a space. I have a space only 3-4 GB. I am facing issue with my other software. You see my computer, local disk C 3 GB.
Sir, it's only 32 KB file actually.
Okay, no worries. Okay, I think that it is long file. So today or in the next class, Amit, is it possible?
Okay. Yeah. Okay.
Next class. Okay. Yeah. Or you can send me. I will check and I will call you once I get free time. Okay.
Okay.
Sir, if you could show the crack step.
Say again.
After installation. Sir, if you could show the crack step after installation, like I did the installation with the antivirus
Please
off
discuss
and
with
internet
Numan.
off.
Numan was telling to turn off the firewall. So please discuss with Noman. Noman, could you help Rahul for this?
He left the ship, I guess.
No worries. So I will, you can approach Noman. He will help you. Okay, Rahul.
Okay, sir.
Okay, so we will practice and share if any problem is faced from our side, then we will share the problem.
Yeah, sure.
Okay.
Okay, thank you. Thank you for your
Thank you, sir. Thank you.
valuable time. Thanks, sir.
Thank you.